Okay, so this is going to be Algebra 2, Lesson 4-4. We are on exponential relationships. That means we are smack dab in the middle of our unit. We are now on standard L, exponential growth and decay. All right, so exponential growth. What does that look like? Think of it like a virus or some chain email where one person sends it to two people and then two people send it to two people and then it gets out of control really fast. And you can change the rate here. What if one person sent it to 3 people? What if one person sent it to 10 people and they all sent it to 10 people and 10 people? I think within the 7th stage you have now hit every single human on the earth. So it can get out of proportions really, really quick. So let's actually analyze that diagram. So let's call this stage 1. Stage 1. So that's x equals 1. How many people are now in that step are infected? I care about how many more are infected if this was a virus. So there's only 1 infected at stage 1. In step 2, I mean, there's a total of 3. I don't care about the total as much. I want to know how many more were infected. There are now 2 people infected. At stage 2, there are 2 people infected, or 2 computers infected. At stage 3, there are now 4 more computers infected. And that can go on, and so on stage 4, this is going to be 8. Can you guys predict what it's going to be at 5?
16.
16, yeah. You guys already saw the pattern. That's awesome. And what does that look like on a graph? So maybe I should make this graph bigger. I'm realizing that now that if I make this graph mega graph, it'll be a little bit more accurate. Oh, nope. Let's keep you straight. All right, so I have my x, I have my y. So we'll say that's 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Okay, so we'll say, sure, that looks like a good 1. Actually, let's scale this by, it's a good number to scale by. It eventually gets up to 16. Let's scale by 3s. 3, 6. Obviously, this is not proportional now. The scaling is different per axis. 9, 12, 15, 18. And this is just a rough graph. It doesn't have to be perfect. So at stage 1, we'll make this in a different color now. There was 1 person infected, right about there. Stage 2, there were 2 people infected, a little bit below 3. Stage 3, there were 4 people infected, a little bit above 3 now. Looks like a line. Maybe it just ends right here. Stage 4, there's 8 people. All of a sudden it jumps all the way up here, right below 9, and at stage 5, it jumps all the way up here to 16. And if I were to continue that line, it would go in a pattern that looks similar to this. It goes, it's a curvy line. Okay, I can do better. You guys can try to do better too. So where does it start here, by the way? Where is 0? Is it 0, 0? It might be. I guess it's hard to say. I would say at stage 0 is probably a half.
That's not how it works. You can't affect half a person.
Possibly not 0, but very close to it or something. I forget.
So actually, it's pretty easy to tell, right? I'll show you in a table how we can actually figure it out. So it goes up and up and up forever that way. Because if I go backwards to step 0, if I'm multiplying by 2, down, 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 multiplying by 2, I just go backwards. Divide by 2, divide by 2, divide by 2, divide by 2. So at step 0, there should be a half.
I know what the equation is.
You know what the equation is?
I think it's going to be 2 to the x minus, or 2 to the x minus 1.
To the power of x minus 1. So we plug in 1. Yeah, that's the equation. I can give you another equation that's the same equation as this one, but it looks different. You want to see it? 1/2 2 to the power of x. Oh man, both of those work. I can give you another one that works. I can give you an infinite number that work. You want another one?
Yeah.
Here's another one. 1/4 2 to the power of x plus 1. Oh, whoa, that one works too, Mr. Sindel. Yeah, it's pretty
Can we
cool.
all simplify those to the same equation though?
You could, yep.
So there's only one equation that is the root?
The simplest.
Yeah, it's an opinion-based question. Which one is the most simple? It depends on what you're looking for. Do you want something that doesn't have very many exponents? Do you want something that is only one number for the base? What is your definition? I don't know. Yeah, so all those equations work for this table, this graph, that works. Although, there is a problem here. Because this is not a continuous function. How many people are infected at stage 1.5?
It's going to be 2 to a fractional exponent.
It would be a fractional exponent. But let's say that it was only this case. We were trying to model that case. Then there is no such thing as 1.5. And our graph, I mean, it shouldn't have any line. It's just a bunch of points. Then we can approximate with a line where it intersects some given integer for x. But yeah, just kind of an interesting distinction between our equation, which is continuous. These equations will produce a line, but in our representation, you can't have a non-integer for x. And therefore, you can have a non-integer for y too, because you can have a half. But that's kind of getting on a tangent. So let's analyze a table. Table. What is that in Spanish? Cuadrado? Or is that just square? Mesa? Do you actually use mesa in math? So if I have a table, I should probably use my straight line to make everything nice and neat. Gigante table. If I have my table, and we'll say same variables, x and y. Are you guys making your curly x's now? So this number, we're going to make two tables right next to each other. If I have 1, 2, 3, 4, and it doesn't really need to go on farther than that. Let's just start at a random value, 3. And then it goes to 6, and then it goes to 12, 24, 48. The way to analyze this is saying, okay, what am I doing to get from here to here? What is the number? Not the number. What is the operation that I do? Do I add 1? Do I times 3? Do I divide by something? And you guys can correctly say that this is doing what?
It's just doubling.
Just doubling, yeah, timesing by 2. And you times by 2 every step. So times 2, every step you're multiplying by 2. All right, so as long as you're going in order, the x's are given in order, and as long as you're going down and you're multiplying by a number that's bigger than 1, that's going to be growth. So we'll make a note here. This table represents exponential growth. Exponential growth, because this number is greater than 1. And I think this number actually has a name for it, and that is the multiplier. These numbers here, we'll call this the multiplier. The multiplier. So exponential growth has a multiplier that is greater than 1. Not equal to 1, because if it was equal to 1, then you would have a linear equation. Okay, and now let's take a look at the table for exponential decay. It's the opposite, so exponential decay. And again, we're going to analyze the multiplier here, so we can write the multiplier. So make another table. So again, we'll start at x equals 1, just kind of by choice, out of habit. That's not an x. X and y. We'll say x is 1 and y is, I'm feeling like a 64. And then 2, we'll make this a nice and easy one. We'll say 32, 3, 16, 4, 8, 5 is going to be what? 4. Yep. So every time you're going to always assume multiplication. I know I said just what operation you could say, oh, well, that's dividing by 2. But if you always say you're multiplying, we'll call it the multiplier. If I have to multiply by something, what am I multiplying by? Say it again, Ben?
0.5.
0.5, yeah. 0.5 or 1/2. So times a half times 0.5. It doesn't matter. In this case, the multiplier is, technically it's between 0. Sorry. The multiplier is greater than 0, but it's also less than 1. It's some fraction. If you're multiplying by a fraction, you have exponential decay. If you're multiplying by something greater than 1, it's growing. Easy peasy. All right, let's take a quick sketch of their graphs and talk about how to find multipliers from a rate. And we actually get to do some applied problems in the very near future, which is pretty fun. So I might need another one of those. So make just like a really quick axis. Let's only deal with the first and second quadrant. I'm just going to deal with the first quadrant for my graphs. It's going to be easier that way. So if I have something that looks like this, that's going to be growth. And if I have something that looks like this, okay, I'm trying here. That's going to be decay. We'll do capital DK. You are now familiar with the table and the graphical representation of growth and decay. By the way, how do I find the y-intercept? It's a lesson that I'll actually hit on tomorrow, but can you tell how to find the y-intercept from an equation, if I gave you an equation? Okay, it's fine. It's a topic for another day. Last thing I just want to talk about, and then we can finish the notes, is finding multipliers. By the way, these were graphs. Finding multipliers. All right, so I'm going to tell you that we have a 70. Let's do a growth example. So this is going to be a growth example and a decay example. I'm going to say something like 7% growth. I need to find the number that I multiply by in this table for a 7% growth. What do I multiply every time?
1.07.
That is correct. And I'm going to write it down here to show you the process to make sure that we understand how to get that. Multiply by 1.07. The answer here is you make sure that this is a decimal. So the decimal is 0.07, and then you do 1 plus the decimal to get 1.07. Perfect. So you multiply by 1.07 every time, and that's 7% growth. All right, let's talk about 8% decay. All right, do we have a guess for what the multiplier is here?
92, or yeah, 0.92.
Yeah, 0.92, and again, it's from the decimal of 0.08, and then you do 1 minus the decimal. Minus for decay, growth is plus. Why did I write decimal? Perfect, and that's a multiplier that you will need for our equation building, which happens, when does that happen? Tomorrow. Today is just finding that, the growth rate, or the multiplier, sorry. So 1.07 is the multiplier for growth, 0.92 is the multiplier for decay. And that is all I have. Go ahead and write your summaries. You guys want to say hello or goodbye to Claire?
Bye.
Bye, Claire.